Greetings again from Rescue Shuttle Control. Our telemetry readings indicate that you're doing very well in getting together all the components necessary to finally get your power systems up and running. As a matter of fact, because of your success in getting the analog light detection, the serial monitor, and the pulse width modulated LED controls functioning properly, today we should finally be able to put everything together and finally complete your battery charging utility. That'll be a big step towards getting you off this planet. We're going to start by reviewing a little bit the familiar pieces from our last few sessions and see how they will fit together into a functioning utility for you today. It'll mostly be review, but we will encounter a couple of new coding twists as we put these things together. As we've added more components and added more functionality, our code has become a little more complicated. And so we're going to have to take some care to make sure that we write our code and organize things in a way that will keep it understandable, and we'll be able to understand it and modify it as necessary. So let's begin with the hardware side of things. Let's begin by looking at our circuit, which should be quite familiar to you based on our last couple of sessions. Let's first have a look at some of the differences, although this will look very familiar to you. Right now, we're going to have two separate parts of our circuit, one which handles the sensor coming from our photoresistor, and the other part of the section in the upper half of the breadboard is the part that we've developed most recently, which controls the 3-color LED. Since both of those circuits need to have access to ground in order to complete their circuits, we've decided here to provide a common ground bus. So we've connected ground from the hero to the vertical blue row on our breadboard. That's our ground bus right there. And so we've used white wires here to indicate the ground connections. So from the ground, we have a white wire that connects us to the low side of our photoresistor sensor, completing that circuit. We have another white wire right here from ground connecting to the ground pin on our RGB light emitting diode. So that's one difference from the way we wired this up last time, just to keep this better organized and a little bit cleaner. Aside from that, the rest of this circuit should look familiar to you. As before, we have our 3 pins, 11, 10, and 9, corresponding to the pulse width modulated outputs going to the red, green, and blue channels of our 3-color LED. As before, each of those 3 channels has a current limiting 220 ohm resistor in series with it. And depending upon how long the red, green, and blue channels are activated during the pulse width modulated cycle, different colors will appear with desired brightness on the LED. Back on the sensor side of things, this is the same circuit that we used before when we were using the photoresistor to provide an input. In this case, the input is going on this yellow wire into the analog input port A0. And as before, we have our complete circuit that goes from steady 5 volts on the orange wire into the photoresistor, then through our 220 ohm resistor, and then finally returning back to ground. And the voltage at the node between our 220 ohm resistor and the photoresistor is the signal which is being sensed by the analog input A0. All right, so hopefully all of the aspects of that circuit are clear and familiar to you by now. So now what we need to do is put together some code that will tie these separate functions, the detection function and the display function together. And along the way, also leverage our knowledge of how to use the serial monitor. So that's what we're going to do next, is turn our attention to our code. We'll begin, as we usually do, by looking at the variables that are necessary to declare that we're going to be using in the course of this operation. And all of these should appear familiar to you. We have on the top here our sensor variables, the sensor pin A0, as we just mentioned, the sensor value, which will have a value other than 0 once we start making measurements. We've got our three output pins that are basically being used to drive the red, green, and blue channels of our LED. And you'll recall from a couple sessions ago that we've defined a number of unsigned int variables that we use to keep track of the running total of elapsed time and the running total of battery charge capacity. So you can review our previous sessions to remind yourself how those are used. In addition, since we do want to do percentage calculations, we have a double precision floating point number that we're going to be using for those calculations as well. So that is hopefully familiar review. All right, let's turn our attention next to the setup routine. The setup routine, again, should be very familiar to you because it's just the same as what we've been using recently. There are two important setup functions that we perform once at the beginning of our run. This is assigning the output functions to our LED pins. So using pin mode on red, green, and blue, that is on 11, 10, and 9, and setting those to output. And then, of course, the other important setup function that we have to do is activate the serial monitor using serial.begin. So again, those are relatively familiar to us, and we can move ahead and start to look at some of the perhaps more novel parts of today's coding. I'll point something out, and that is that as we've been adding more functionality, and as we've been getting a little more involved, our code has been growing. It's been getting longer, and it's also been getting more complicated. And as a result, we want to try and be as careful as possible to organize things in a way so that we don't wind up with something that's unreadable at the end and just sort of looks like spaghetti code. So you'll notice that today we're going to make a little bit more use of separating our code into functions. I've also tried to add comments to clarify things, including just these comments that are simply used as separators to set off one function from another and make it a little bit more readable. So you'll see that the next function that we have set off by comments right here is another familiar one from just our last session. This is our familiar RGB color routine, and it has the function of taking as input desired values of red, green, and blue, and doing the analog write on the corresponding pins. So when you call RGB color at any time with 3 input values, it will turn on the LEDs in the appropriate way. So that one we don't have to dwell on too long because we've already worked with this and understood it previously. The next function, the next custom function I'm going to discuss, involves something we haven't really done before. Up to now, whenever we've defined a new function, it's been a function of the type void. And void just simply means that it does not return a numerical value. But sometimes functions don't simply perform a function, but they also return some number as a result. And so our next custom function that we're going to introduce here is such a function. Instead of being type void, it's type double, which means that whenever we call this function's name is getBatteryPercentage, it comes back with a double precision number as its result. You'll see how we use that in the subsequent code in a moment. In this case, our function, getBatteryPercentage, does a pretty obvious thing. And it's easy because this particular function is going to only consist of a single line. There's just one line of code necessary in order to get battery percentage as we want it. So let's go ahead and enter that single line and see what it does. It says return. Well, return is what happens when a function returns a value back to whoever called it. And so what number are we returning? Well, we're returning the number that results when you take battery level, convert it to a floating point number, divide it by battery capacity, also converted to a decimal number, and then multiply by 100. Okay, so we did that before in our previous session. We just didn't put it in an outside function. And so now, for the purposes of modularity and clarity, we've decided to take that calculation of battery percentage and sort of compartmentalize it into a function that we can call whenever we want. So that's a new thing, our custom function to basically calculate battery percentage. Next, we'll have another function. This one will not return a value. It'll be a void function, but this will use the previous function in doing its job. This is the longest sort of chunk of code that we're going to devise today. And so we'll take a little bit of time in carefully working through all of the parts of it. So you can see that the name of it is show battery percentage as opposed to get battery percentage. Now we want to show this to our user. And we're going to show battery percentage in both the text form coming through the serial monitor and in the visual form through the color of the LEDs. So in order to do this function to show battery percentage, the first thing we got to do is find out what the battery percentage is. So the very first thing that we'll do is call our new function, get battery percentage. And the syntax for that is very simple. We take our variable, our double precision variable %full, which you'll remember we defined way up here at the top. Here it is declared as a double precision number, a double precision variable. And when we call this, we just simply say set %full equal to the returned value of get battery percentage. And every time we call this, %full will be set to the current value calculated by get battery percentage. And we'll always have an up-to-date value of %full. All right, that's clear enough. The next thing that we're going to do is take that newly acquired information and we're going to print it to the serial monitor. And now I'll borrow code that we've already written and should be familiar with if we go back and review a couple sessions ago. So I'm going to borrow that code and insert it right here. And I'll just remind you that in order to make our serial output a little bit more legible, we put in both the time information, a little bit of text, and the percentage so that we had a reasonably legible output. And you hopefully will remember this. The first thing we do is we print to the serial monitor the current value of the time. You'll see a little bit later if you've forgotten how we know what the current value of the time is, but it's in this variable ticks. Next, we print out a little caption that says milliseconds, charge at, space, and then finally we print out %full. the value of the charge percentage that we just calculated up here. Finally, we finish up with printing a percent sign and a line return, and we're ready to return back and wait for further instructions. So this is what show battery percentage does as far as the serial monitor is concerned. But remember, we're not done yet, because we also, every time we come into this function, we also want to update the status of the color LEDs. So we have another chunk of code to insert before we're done. And this is what that code is. So we'll go ahead and right after the serial monitor block, we'll insert this block of code. And you can see that it involves some conditional tests, some if and else tests. Now, first off, let's just see what we're asking at the very beginning. We're saying if percent full is greater than 0, well, it's always going to be greater than 0, right? Well, if it's greater than 0 and it's less than or equal to 25, that means we're in the lowest 25% of charge state. Let's call RGB color and set the LED to pure red. So that'll be sort of the low charge indication. It's between 0 and 25%. By the way, I just want to point out to you, in case we haven't discussed it adequately before, this greater than sign and this less than or equal sign, these are what we call tests. They test to see whether or not percent full is greater than 0 or whether it is less than or equal to 25. And the result of that is either true or false. The double ampersand here is a logical AND. So this whole expression will only be true if both of these things are true. If both percent full is greater than 0 and it's less than 25. We'd get a different result if, for example, instead of putting a logical AND here, we put in a logical OR, because then this would be true if either one of those was true. But in this case, we want it to be both greater than 0 and less than 25, in which case, turn the color to red. Next, let's see what happens if this fails, if this is not true. Else, if percent full is between 25 and 50. So greater than 25 and less than or equal to 50%, in which case we change the LED color to this mixture of red and green, which sort of has a yellow appearance to it. You can customize this in any way that looks good to you. Then, if that fails, if the two preceding tests fail, we can ask, well, what if it's between 50 and 75? So in this case, we've chosen to make the color corresponding to between 50 and 75, a sort of bluish green color, a mixture of the green and blue channels. And so we'll use that as an indication of almost charged, but not quite. Finally, well, actually above 50%. Almost charged and not quite will come with this last test, which is between 75 and 100. So between 75 and 100, we'll turn on all three channels at 125, which should approximate a white color. And that will be the end of what we're asking this function to do. There's more logic that we're going to have to deal with once we've reached 100, because we don't want to go over 100. But that will be a job outside of this function, outside of show battery percentage, because show battery percentage is really just concerned with an update during the process of charging. All right, hopefully that's all pretty clear, and we've got a reasonably good understanding of how that's accomplishing its job. And since we've farmed out a lot of these pieces of these tasks to separate outside functions, we've unloaded a lot of the stuff that might otherwise be filling up our main loop function. So in the process of expanding our code, we've avoided bloating the loop function too much. And so it looks actually very familiar and relatively slim. As a matter of fact, if you look at it, it'll look very much like what we've done in our previous sessions. Loop, now the one which is going to execute repeatedly, begins by making the key measurement that drives all of this. Sensor value is obtained from an analog read of our sensor pin, analog 0. Once that value is set, we can go ahead and increment the battery level. Remember, we take each sensor value and add that to the previous battery level so that it's rising over time. We do the same thing with our time variable. So whatever our wait time is, in this case, I think it was, let's see, our wait time was 100 milliseconds. So every 1/10 of a second, we will increment ticks by an appropriate amount. And now we go ahead and do the test to see whether or not it's time to stop charging or not. And so here within loop, we have the test that checks to see if battery level has reached battery capacity. That is, if battery level is greater than or equal to battery capacity, this is true, and we'll execute the terminal block of code right here. However, if we are not fully charged yet, that is, if this is false, battery level is not greater than or equal to battery capacity, then we jump down to else. And else simply calls our show battery percentage. It updates the serial monitor, and it also updates the LEDs, and then we wait for the desired delay time, and then repeat over and over again. So this will continue to update the serial monitor and the LEDs continuously until this test succeeds, until battery level reaches battery capacity. And you can see what we've done at this point is set it up so that it will not continue to rise beyond 100%. In this case, what we do is we print out the time, we print out fully charged now rather than a percentage value, and then we lock battery level at battery capacity. We turn the timer ticks off back to 0, and we set the RGB LED color to solid green. Solid green will be our indication that we've reached the end and we're done. And we just threw in a long delay here of 30 seconds so that it will sit there with the green LED on for a substantial period of time. And that completes the logic of our code for today's project. With that, it's time now to see if it all works. We've put a lot of effort here into trying to design this code to function along with the circuit and to be reasonably understandable. So let's check and see if we made any mistakes. Let's check and compile it. Compiling it shows no errors, so that's a good sign. As soon as I upload this code and start running it, it will start the charging cycle going. Since our photoresistor is in the light right now, it will start charging. I think what I'm going to do is I'm going to begin by covering up the photoresistor so that it will not immediately start charging. And then we'll uncover it and see whether or not increasing the light that's falling on it changes the charging rate. All right, so let's go ahead and upload the code and see what we get. Code uploading. And we have a red LED, and you can see that our serial monitor is in fact showing us a slowly rising charge. We're in the dark, and so we're only up to 1% at this point. When I uncover the photoresistor, we should see a jump in the rate of charging. And remember, when this charge reaches 25%, we should expect to see the red LED shift to a yellow color. So let's uncover the sensor, and we can see the charging rate is going up faster now. We're up to 10% already. In a few more seconds, we should be crossing over the 25% threshold. So there's 20% and 25, and we've just switched to yellow. So that's appearing to be working as we wished it to work. I can speed it up a little bit here if I shine a flashlight on this and bring this up in speed. There, we've already switched over to the 50% level. Once we reach 75%, we should switch to white. Let's see, that should be coming up momentarily. 70, 71, 72, 73, 74, and there we go. We're in the white LED mode now. And so shortly, we'll reach 100%, and we'll see if our termination works as desired. Here's 92, 93, 94, and there we are. We're at fully charged, and the LED has switched to green. So this is great. This means that we've succeeded in building our battery charging utility, and we're ready to move forward with more systems on our rescue shuttle. But we've solved one of our big problems, which was how to manage power. With that, I encourage you to work on this yourself, customize this as you find to be helpful or fun, and we'll tackle our next problem soon. Until next time, remember, build everything and invent safe.